Section 6.1 is systems of equations in two variables. We've actually solved some systems of equations, we just haven't called them that. So let's take a look formally at what this means. A linear equation in two variables can be written in the form ax plus by equals k, where a, b, and k are constants. So x and y would be the variables in this equation, and a and b cannot be equal to 0. A pair of equations is called a system of linear equations because they involve solving more than one linear equation at the same time. Whenever you're solving a system of equations, it's possible to have equations with more than two variables. The number of equations must be equal to the number of variables if you hope to solve a system of equations. A solution to a system of equations consists of an x value and a y value if you only have two variables that satisfy both equations simultaneously. That means that they have to make both equations true at the same time. The set of all solutions is called the solution set. Typically, this is going to be an ordered pair. For example, if you're graphing two linear equations, those two lines will intersect at a single point. That point of intersection is called the solution to that system of equations. When this happens and we have only one solution, we call this a consistent system with independent equations. Another thing that can happen when you're graphing two lines is the two lines could actually coincide with each other. If this happens, you have infinitely many solutions, but you can't just write all real numbers for your answer. Your solution is going to be every point that's on the equation of this line. And we'll do an example where I show you how you would write up your answer. Another thing that happens when you graph two lines is that the two lines could be parallel. If this were to happen, these lines would never intersect, and we would say that there's no solution to this system of equations, and we call that an inconsistent system. In example 1, I ask you to graph each system of equations and find any solutions. I've gone ahead and provided you with the graphs to save us some time, but you guys know how to graph linear equations already. Identify the system as consistent or inconsistent. If the system is consistent, state whether the equations are dependent or independent. We have independent equations if there's only one solution. We have dependent equations if our lines are actually collinear, if the lines lie on top of each other. So in this first one, we have the system of equations. These two equations considered together is the system of equations. If I were to solve this first equation for y, I would end up with y equals x minus 2. That's the graph of this blue line right here. If I solve this equation for y, I get y equals x plus 1. That's the graph of this red line. Because these two lines are parallel, they're never going to intersect, and we would say that there's no solution, and that means that they're inconsistent. This is an inconsistent system, and that implies that there's no solution to the system of equations. In part B, we have this system of equations, these two equations taken simultaneously, and when we graph both of these equations, and we can do that by solving each of these equations for y, we end up with these two lines, or these two linear equations, intersecting at a single point. That means that the system is consistent, and because there's only one solution, we say that this is independent. And our solution would be the point at 1, 2, because that's where the two lines intersect. Now, it's important that you check your answers, and we can check this first equation by plugging in a 1 for x and a 2 for y and see if we get a true statement. So on our first equation, we would have 4 times 1, because 1 is what x is equal to, minus 2, because that's what y is equal to, and what we want to know is that equal to 2, the right-hand side of this equation? Well, 4 times 1 is 4, 4 minus 2 is 2, and we do get 2 equals 2. So that checks out. Then we've also got to check the second equation. We'll plug in a 1 for x and a 2 for y. So we get 1 minus 2 times 2, and we want to know, is that equal to negative 3? Negative 2 times 2 is negative 4, and 1 minus 4 is indeed negative 3, so negative 3 equals negative 3, and this checks out. So we would say that this is our solution to this system of equations. This is how we would solve an equation graphically. On part C, if I solve this equation for y, I get y equals 2x minus 1. Here, if I solve this equation for y, I also get y equals 2x minus 1. Because there's an infinite number of solutions, we would say this is a consistent system of dependent variables. Your solution is going to be the set of all points x, y, an ordered pair, given the condition that y is equal to 2x minus 1. What that means is that any point along this line will make both of these equations true at the same time. There's several methods you can use whenever you're solving a system of equations in two variables. The first method we're going to look at is substitution. In the substitution method, the first thing you want to do is choose a variable, just one of them, out of the two equations, and then solve the equation for that variable. Just isolate a variable. Then you're going to substitute the result you got from step 1 into the other equation and then solve for the remaining variable. And then we'll go back and use the value from the variable in step 2 to determine the value of the other variable using what we got in step 1. So let's look at this substitution method. In example 2, we're told in the first quarter of 2016, Apple Corporation sold a combined total of 90.9 million iPads and iPhones. There were 58.7 million more iPhones sold than iPads. Part A asks us to write a system of equations whose solution gives the individual sales of iPads and iPhones. Our first step is going to be identifying our variables. Let's let X be equal to the number of iPhones sold, and we'll let Y be equal to the number of iPads sold. In part A, we're told to write a system of equations whose solution will give us the individual sales of iPads and iPhones. So we use the information that we're presented with. First, we're told the total sales was 90.9 million iPads and iPhones. So if I take the number of iPhones plus the number of iPads, we can set that equal to 90.9, and that will give us our answer in millions because this would be measured in millions. Our next equation we can write using this 58.7 million, and we were told that more iPhones were sold than iPads. So if I take the number of iPhones minus the number of iPads, that will give me the 58.7 million. This would be my system of equations that I would want to solve. In part B, we're told to solve this system of equations. In order to solve this system of equations, I'm going to number my equations. I'll call this first one right here equation 1 and this one equation 2, just to make it easier to talk about. I'm going to isolate X in equation 2. Because it's easy to get this X by itself, I'm just going to add Y, and that way I don't have any negatives to worry about. That's my first step. Isolate one of the variables. In order to do that, then I need to add Y to both sides, so now my new equation 2 becomes X equals 58.7 plus Y. So in using the substitution method, I'm going to take my equation 1, and in place of X, I'm going to plug in what I said X was equal to by isolating the X in equation 2. So I'm using equation 1, and instead of writing X, I'm going to write 58.7 plus Y, and then plus Y equals 90.9. Do you see how this is what I got when I solved equation 2 for X? I then substitute that into equation 1 in place of X, and now I've got one equation with one variable, and I can solve that. So what I'm going to do is I'm going to go ahead and combine my like terms here. And when I do that, I get 58.7 plus 2y equals 90.9. Then to get the y by itself, I subtract 58.7 from both sides. And when I do that, I get 2y is equal to 42.2. Then we divide 2 by both sides of the equation, and I get y is equal to 21.1 million, and y we said was the number of iPads. Now, in order to figure out how many iPhones we had, I take this 21.1 million and plug it in right here in place of y. So X, we say, will be equal to 58.7 plus 21.1, and that gives us 79.8 million iPhones. If I were writing my solution as an ordered pair, I would write 79.8, comma 21.1, but it represents the number in millions of iPhones and iPads that were sold in 2016. Part C says, is your system consistent or inconsistent? If it is consistent, state whether the equations are dependent or independent. Because I had only one solution in Part B, that means that my system is consistent and independent. Example 3 says, if possible, solve each system of equations. We're going to solve these systems using substitution. In order to help us do that, I'm going to number these equations right here. X squared plus y equals 1 is our first equation, and x squared minus y equals negative 2 is our second equation. Using the substitution method, I need to pick one of the variables here to get by itself. Well, this one I'm going to get by itself by adding y to both sides, so I'm going to say in equation 2, I could rewrite that and say y is equal to x squared plus 2. That X squared plus 2 then is what I'm going to substitute in place of y in equation 1. So equation 1 becomes x squared plus 2 equals 1. So I have this x squared plus 2 that I've dropped in place of y in equation 1. Now I combine my like terms, and x squared plus x squared is 2x squared plus 2 equals 1. Then I need to subtract 2 from both sides of this equation, and I end up with 2x squared equals negative 1. Here I could stop and say that there's no solution because I have a x squared equal to a negative, and when you square a variable you get a positive if you have a solution. So I would stop right here and say that there's no solution and we have an inconsistent system. For the system of equations in part B, I'm going to start the same way. I'm going to number my equations to make it easier to discuss. So I've got to pick a variable to isolate. I think it'll be easier to get x by itself here because all I got to do is add x to both sides of the equation and add 5/2. So when I solve equation 2 for x, I get x equals 2y plus 5/2. Now I'm going to drop in this 2y plus 5/2 in place of x in equation 1. So in equation 1, I've got 2 times 2y plus 5/2 minus 4y equals 5. Because I have only one variable in one equation, I do stand a chance of being able to solve this. I need to first distribute this 2 across the parentheses, and when I do that, I get 4y plus 5 minus 4y equals 5. I can combine like terms here, and when I do that, I get 5 equals 5. Because this is a true statement and all of the variables have dropped out, that means that I have a dependent system of equations and I have an infinite number of solutions. How I would write my answer here is my solution would be the set of ordered pairs x, y, given the condition that, and then I just pick one of the variables to solve for, and I could say x is equal to 2y plus 5/2. This is one way to write your final answer. Another method available to us for solving systems of equations is called the elimination method. This method is based on the property that equals added to equals are equals. What that means is if I have a equals b and c equals d, then I could add the left-hand side of the equation together, and that would be equal to the sum of the right-hand sides of the equations. The goal of this method is to obtain an equation for which one of the two variables has been eliminated. That's why we call it the elimination method. In example 4, we're told to solve the system of equations using the elimination method. Your first step is to pick a variable to eliminate. Once you pick that variable to eliminate, you perform the operations necessary in order to eliminate that variable. Then you solve for the remaining variable. We use the solution from step 3 to find the value of the variable that we eliminated in step 2, and then we check our answers. So in part A, I have to start by finding a variable to eliminate. For this problem, I think it's going to be easy to eliminate the x's because all I got to do is add the two equations together. So how I would do this is I would take equation 1 and I would add to it equation 2. And when I add these two equations together, 2x minus 2x is going to cancel out. Negative 3y plus 4y is y, and negative 2 plus 4 is 2, so I get y is equal to 2. I take my answer from this step and I plug it back into one of the original equations in order to find x. And I'll use equation 1 in order to find x here. So that means I've got 2x minus 3 times, in place of y I'm going to plug in the 2, equals negative 2. And that gives me 2x minus 6 equals negative 2. If I add 6 to both sides, I get 2x is equal to 4, and that means that x then would be equal to 2. So my solution here would be the ordered pair 2, 2. And you could do a quick check of this and plug in a 2 for x and a 2 for y, and you'd see that you get 4 minus 6 is negative 2, and negative 4 plus 8 is 4. So this works out, and this would be our final answer. On part B, the first thing I need to do is pick a variable to eliminate. It looks like the x's or the y's would be easy to eliminate. We eliminated x last time, now let's eliminate y. Well, in order to get the y's by themselves, I just need to add both equations together like I did before. So I'm just going to write down both of these equations as I see them. That gives me 3x minus 2y equals 1, and negative 3x plus 2y equals negative 1. And when I add the two equations together, everything drops out and I get 0 equals 0. This is a true statement. That means that any value will make this equation true as long as it's a point on the equation of one of these lines. That means that I have a consistent dependent system and it has an infinite number of solutions. Those solutions will be the points x, y, such that, and then I just pick one of the equations of the lines. I could say 3x minus 2y equals 1, and that would be my final answer. When you're solving a systems of equations, the goal is to find the values that make the equation true. If all of the variables drop out and you're just left with a true statement, that means you have a dependent system. On part C, it looks like I can do the same thing and add both equations together, and when I do that, the x's are going to cancel out, the y's are going to cancel out, but now I end up with 1 plus 3 is 4. This is a false statement. If you have a false statement, it means you have an inconsistent system and there is no solution, or you could write the solution as the empty set. I'm okay with you expressing yourself either way. On the last example, I wanted to show you some problems where you got to do a little bit more than just add the variables together. So in part A, I need to pick a variable to eliminate. Honestly, it doesn't matter if I choose the x's or the y's, so I'm going to say let's eliminate the x's. Well, in order to eliminate x here, I need one of my x's to be positive and one of my x's to be negative. So I'm going to say let's multiply this first equation by 3, and we'll multiply the second equation by negative 2. That'll give me a positive x and a negative x. So I'm going to distribute this 3 across the entire equation, and that's going to give me 6x minus 9y equals 0. And then I multiply this second equation by negative 2 and I distribute that negative 2 across to every term in the equation. Negative 2 times 3 is negative 6x, negative 2 times negative 2y is plus 4y, and negative 2 times 5 is positive 10. Now I just add my equations together, and when I do that, the x's are going to cancel out, and I'm left with negative 5y equals 10. In order to get the y by itself, I'll divide both sides by negative 5, and that gives me y is equal to negative 2. Once you know what y is equal to, you can then go back to one of the original equations and solve for x. I'm going to use this first equation, and that means that I get 2x minus 3 times negative 2 equals 0, and that's going to give me 2x plus 6 is equal to 0. So when I subtract 6 from both sides, I get 2x equals negative 6, and that means that x is equal to negative 3. So my solution to this system of equations is going to be the ordered pair negative 3, negative 2. Now you can check your answer by going back to the original problem and plugging in the values that you got for x and y. So that would be 2 times negative 3 is negative 6, minus 3 times negative 2 is negative 6. Subtracting a negative is the same as adding, so that gives us 6. That gives us negative 6 plus 6 is equal to 0, and that's true. If it makes one of the equations true, it's going to make the other one true, so we're going to stop with that. Now let's look at part B. The first thing I need to do is pick a variable to eliminate. Here I want to eliminate the y's because I have one that's positive and one that's negative, so half the work is done. I would like to avoid multiplying by negatives if I could. So in order to get the y's to drop out, I need this to be multiplied by 7 and this to be multiplied by 5. So I'm going to multiply this first equation by 7 and I'm going to multiply the second equation by 5. And when I do that, that's going to give me 21x minus 35y equals 77. And when I multiply the second equation by 5, that gives me 20x plus 35y equals 5. Now I just add the two equations together, and when I do that, that gives me 41x equals, the y's are going to drop out, and then that gives me 82. Then I can divide both sides by 41 and I get x is equal to 2. Once I know an answer for x or a value for x, I can go back to the original problem and plug in a 2 for x and solve for y. So I'm going to choose the second equation where the y term is negative. So that's going to give us 4 times 2, because x was 2, plus 7y equals 1. So that's going to give us 8 plus 7y equals 1. If I subtract 8 from both sides, I get 7y equals negative 7, and that means that y will be equal to negative 1. So the solution to this system of equations is going to be the point 2, -1, and this would be a consistent independent system. It's a good idea to check your answers, and you can check them by plugging in a 2 for x, a -1 for y, and see that you do get a true statement. 3 times 2 is 6, plus 5, because when you plug in a -1 for y, that gives you a positive 5, and 6 plus 5 is 11. And this wraps up section 6.1.